Alright, in 11.3 now we're going to talk about how sampling distribution models work, and to start with we're going to talk about standard error. And standard error comes up when we try to find the standard deviation of a sampling distribution. And so if we have a sample proportion p hat, so recall p with the hat above it means that it's a proportion of a sample, then our standard error is standard error of p hat is equal to p hat times q hat. Now remember, those two are related, so if we have a proportion of say 60% of people respond yes or something like that, then q hat represents the people who responded no, so we can only answer yes or no. So p hat, if p hat's 60, q hat is 40. So those two are always related by 1 minus the other quantity. Divided by n. N is the size of our sample, how many people we talk to. The sample mean, so this is if we're looking at average values or mean values, the standard error becomes standard error of y bar is s, our standard deviation, divided by the square root of n, the sample size. So for means, we're talking about things like, we'll say we're talking about average height or something like that. Then we can find a standard error for that height based on our standard deviation, whatever that might be, divided by square root of n. Okay, the sample proportion and the sample mean are random quantities. We can't know what our statistic will be because it comes from a random sample. So again, we're going to be looking at random groups of people or objects, and we're going to take some measurements. The couple truths about this type of sampling are that they arise because samples vary. So for example, if I want to know the height, the average height, or the mean height of groups of DMAC students, I might take classes. So I might look at 10 different classes, and each class might have between 20 and 30 people. And I might look at, and I want to spread that around. So I want to look at, let's just stick with Ankeny campus. So I want to look at classes in different buildings at different times throughout the day. And as you might imagine, the mean height of each of those samples is going to be different a little bit. We'll actually talk a little bit more about this with a picture here in the next slide. And then basically the central limit theorem, which we talked about in previous sections, tells us that we don't have to do a bunch of samples. We don't have to really actually go and find 10 or 20 different samples of students on DMAC's Ankeny campus. It's going to tell us that if we were to do that, we know what the results should be, and we'll see that here on this next slide. So basically this slide says we don't know the blue line. We don't know the population distribution of heights for DMAC Ankeny students, but we'd like to know that. We'd like to know the mu, which is the mean, and we'd like to know the sigma, which is the standard deviation. So what we could do is we could take a bunch of samples, like I just said. Find 10 different classes, and each class we measure will have a histogram like the one shown here, where each class has a mean height, y bar 1, and a standard deviation. So in this example, we have most people over here, and then a few really tall people over here. Then we can measure another class and do the same thing, a second class, a third class, a fourth class, etc. But what the central limit theorem tells us is that the more classes we look at, we can actually plot their mean values in another histogram. So think of this as a histogram of histograms. So before, each histogram had one y bar, and we might have 10 or 20 of those, and then we're going to plot a histogram for those. So we're going to say, oh, here's several y bars that fit into this height range. Here's another group of y bars that fit into this height range. And central limit theorem tells us that those values, a histogram of histograms, will look like a normal curve. In fact, it will be very normal, very symmetric, and we'll get a very nice measurement of the mean height of all the mean heights. And so what we do is we can find the properties of this normal curve, and we'll find the standard deviation of all the different y bars, and that should equal the sigma of our population, so the standard deviation of heights of all DMAC students, divided by the square root of n, the sample size for our samples that we use to find these histograms. And then we can approximate the population normal curve with this data. So we know that the mu should be the center of this normal curve, the mean, and then our standard deviations go by factors of sigma over root n. Now let's think about this. We don't know the sigma of the population, but we're approximating it using all these normal curves. So now, it used to be the standard deviation of a population was just sigma. So this square root of n divisor, imagine that's not there. Now that says, let's say the average height or the mean height is 5'10", and with a standard deviation of 6 inches. Let's just use that. It's probably not, those numbers probably aren't right, but let's just use them for simplicity. 5'10" is the mean, sigma is 6 inches. This says if I start breaking my population into a bunch of samples, into a bunch of smaller groups, then we can imagine that each average height is going to be pretty close to one another. So you might have one room where the average or the mean height is 5'7". Then you might have another room where the average or mean height is 5'8". Then you might have another room where the average or mean height is 5'9". Now those three means are all differ by 1 inch. So what you get is you get a much smaller standard deviation. So we go from 6 inches for our standard deviation of all the people down to 1 or 2 inches for our samples. And hopefully if you think about that, that makes sense. If I grab any random group of people, those small groups are probably going to be much closer together in height than if I look at a large group where I could have really short people or really tall people. And so that's where that divisor of square root of n pops up, and it actually makes our standard deviation much smaller. So like I said, we don't typically know the sigma of the population, so we're going to estimate it with the standard deviation of one of our real samples. So we're going to use standard error instead. So we're going to say, okay, we know the any given sample of 20 or 30 people, we can easily measure y bar, which is just the mean height, and we can easily measure the standard deviation of those heights of those 20 or 30 people, which we call lowercase s. So s we know the sample size, square root of n, so we can use this standard error to estimate the sigma. And that's going to do it for 11.3.